A single decision tree is wonderfully easy to read, but it's twitchy. Change just a few data points, and the whole tree can flip to a completely different shape. The fix is beautiful in its simplicity. Don't grow one tree, grow hundreds, each one a little different, and let them vote. That's a random forest, and it's one of the most reliable models you can reach for. Remember the weakness of a lone decision tree. Let it grow deep and it overfits, memorizing the noise in the data. One tree is really just a single opinion, and a single opinion can be confidently strangely wrong. So here's the first trick, and it's called bagging. We build many trees, but we never show them all the same data. Each tree gets its own random sample of the rows, drawn with replacement, so every tree sees a slightly different slice of the world and grows up a little differently. There's a second sprinkle of randomness too. At each split, a tree is only allowed to consider a random handful of the features, not all of them. This stops every tree from leaning on the same one dominant feature and keeps the whole forest genuinely diverse. Now to predict, we run the new point through every single tree, collect all of their votes, and take the majority. For regression, we'd simply average instead. On their own, the trees are noisy and imperfect, but their mistakes point in different directions. So when you pool them, the errors cancel out, and a much steadier answer is left behind. That's the deep idea here, the wisdom of the crowd. A crowd of diverse, independent, slightly wrong models almost always beats any single one of them. The forest keeps all of the trees' flexibility, but throws away most of its overfitting. And as a free gift, the forest can tell you which features mattered most by measuring how much each one reduced impurity averaged across every tree. That feature importance ranking is one of the most useful things you get straight out of the box. In Scikit-Learn, it's almost the exact same code as a single tree. We just reach for random forest classifier instead, with an estimator setting how many trees to grow, then fit, predict, accuracy score, and we can peek at the feature importances. Let's write it. Here's the program, back to a single page, every line in view. It's nearly identical to the decision tree code from last time. Honestly, we're just swapping one class for another. Let's read it through. The imports. Make classification this time to whip up a dataset with a few genuinely informative features. Random forest classifier from sklearn.ensemble, the usual train test split, and accuracy score. We generate a dataset, 500 rows, several features, 2 classes, where only a few of the features are truly informative and the rest are basically noise. It's a nice test of whether the forest can find the real signal. Split 80-20, fixed random state, exactly the same as always. And here's the only real change from last episode. Random forest classifier with n estimators equals 200, that's 200 trees, plus a random state for reproducibility. Then we fit. Behind that single call, it's quietly growing 200 separate trees, each on its own bootstrap sample of the data. Predict and score. And notice the accuracy is usually both higher and steadier than a single tree would give, around 93% here, because all of those votes smooth the noise away. And now the bonus. Model.feature importances gives us a number for every feature. How much it helped across the whole forest. We sort them and print, and the truly informative features rise right to the top while the noise sinks. And that's the random forest, many diverse trees, each a little bit wrong, voting together into something genuinely reliable. It's often the strongest model you can train with almost no tuning at all. Next time, we keep the trees, but build them in a smarter sequential way. That's gradient boosting.